Hey, everybody.
Hi, Professor.
Hi.
So I have some question regarding the homework
Okay.
2B.
Okay.
So I did the code and my code turned out to be a straight line shooting up. So
Okay.
I'm not sure where I did it wrong.
If you send me your code, I can take a look and then I can give you some feedback on that. But just from that, it's a bit hard for me um, to kind of say.
Okay,
Yeah. Why don't you send me your code and then I'll take a look at it.
awesome. Thank you.
Yep. We're starting a new set, so we're starting the lecture notes on 2D diffusion. Yeah. So I think it's lecture notes. Let's see, 05. Mhm. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? How's everyone's long weekend? Short? Yeah. Always too short. Yeah, long weekends are always nice, but then there's always a sadness at the end of the weekend that it's over already. But hopefully, everyone was able to rest up. Um, I actually spent a lot of my day off making juice, actually, because my fiance actually brings home a lot of fruit from work. Because she has a coworker that's apparently he's like 85, and why he's still working at that age, I don't know. But he lives in this retirement home with a lot of other old people, and it seems like all the old people there have their own fruit tree. And so they produce a lot of like lemons and oranges and grapefruits, but it's way too much fruit for old people to eat on their own. And so he regularly gives it out to his coworkers. So I had a huge batch of just oranges and grapefruits and lemons. So I spent most of my day off just turning all of those into juice. So now we don't have a ton of fruit anymore. Now we have a ton of fruit juice. Yeah, it's nice. It's nothing beats a good fresh fruit juice. Okay. And so last time we met a week ago, we had just finished our lecture notes on 1D diffusion. Okay. And so basically what we did was we applied the finite difference method to a 1D diffusion equation, and we saw how we could simulate that in MATLAB. Okay. So this week we're going to take it a step up. And so what we're going to do is we're going to simulate the 2D diffusion equation. Right. And so with 2D, we'll have two different spatial dimensions. We'll have both x and y. And so here's where finite difference really starts to shine, because in 1D problems, you can just solve those by hand, and actually doing the finite difference solution is kind of actually more work. But in 2D, solving 2D problems by hand really becomes really, really difficult. And so finite difference actually ends up being a lot easier for this one. So, starting from this week, you'll really start to see, the power of these methods, and you'll start to produce a lot more, cool looking, interesting plots in MATLAB as probably you might have seen in the homework already. Okay. All right. So before I start, are there any questions I can answer before we get going? Okay. Are you doing the wrong Zoom before this?
Are we using MATLAB or no?
No, today we're not using MATLAB, but we'll use MATLAB on Monday. Yeah.
Cool, thanks.
Mm-hmm. Yeah. Today is just going to be theory, and then Monday we'll talk about how to implement it. Okay. So there's no more questions. Let's go ahead and get started. Okay. And so this is going to be the 2D diffusion equation with finite differences. Okay. All right. So last week we basically worked on an equation that looked like this. Okay. And so we had a second derivative of phi. Okay. And so remember, phi here is our unknown, right? And so phi, we're using that to substitute for temperature or for mass, right? So this is our general kind of conservation variable, okay? And so our equation looks something like this. So we had, a second derivative of phi with respect to x on one side of the equation, and on the right side of the equation we had, our source term, okay? And so this week we're going to kind of supplement this equation and add another derivative in the y direction. And so by taking this to 2D, we're going to add another derivative with respect to y, just like that. Okay. And now our source term here is going to be a function of both x and y. Okay. And so here's just a little bit of trivia for you. So this particular equation right here, where we have kind of two second order derivatives in each direction, and we add them, and on the right side we have some function. This is an equation that actually shows up in kind of mathematical physics a lot. And so this equation has a name. And so this particular equation is called the Poisson equation. Right. The name isn't really that important, at least for this class. But if you kind of move on from this and you study this further, you might see the terminology Poisson equation come up quite a bit. So this is just to kind of let you know what it is. Okay. And we can take actually a special case for this, where if our source term is 0, then we end up with this equation. Okay. And so all I did, from the top equation to the bottom one, is I set q of x and y equal to 0. Okay. And so this, this doesn't always occur, because a lot of times we do have a source term, but sometimes it does. Okay. And the reason I list this out is that this is also another named equation. And so this is called the Laplace equation. Okay. And so just a little bit of trivia for you in case you come across these names, when you're reading a scientific paper or something. Okay. And so, yes. Yes, so they're definitely fundamental to electricity and magnetism for sure. All right, and so the big difference between what we did last week and what we're doing now is that if you wanted to solve these equations by hand, you'd have kind of a really tough time to do that. Okay, and so exact solutions are really hard to obtain. And the reason, they're really hard to obtain is that now, instead of an ordinary differential equation, what we have now are partial differential equations, right? So both of these guys are PDEs. Right? And PDEs aren't normally taught within kind of the, a general undergraduate curriculum. In graduate school, I think, you're required to take some classes, but for undergrads, it's typically not taught. And so if you want to learn how to solve PDEs, you have to take, a full course in this. So and so I know Dr. Weiss, I think, teaches an advanced engineering analysis class. I think it's 431 or something like that. And so, we're not going to solve these by hand because, that class already exists. And so what we're going to do instead is we're going to solve these equations computationally using finite differences. Okay. And so actually, the method that we're going to follow here is actually exactly the same, exactly the same as what we've been doing before. It's just that now we're going to apply the finite difference method twice to two different derivatives here. Okay. And so, the way that we're going to turn this into an algebraic equation is we're going to take both of these derivatives, okay, and apply finite differences to turn it into an arithmetic expression. Okay. And then from there, what we're going to do is we're going to apply that equation to each of the different nodes in our mesh in order to get a set of linear equations that we can solve using MATLAB. All right. Any questions on this so far? Okay. All right. So what you'll see is that conceptually and in terms of applying the method, this is not any different than what we've done before. I think that the real difficulty with 2D equations relative to 1D is that there's a lot more kind of what I call bookkeeping and a lot more infrastructure involved.
So, Professor, so if we're finding like the Laplace transforms.
So this doesn't have anything to do with the Laplace transform. So it was discovered by the same guy, so that's why they have the same name, but they're kind of two different things. Yeah.
Oh, okay. My bad.
Okay. And so you'll see what I mean by bookkeeping in a second. So I think that's generally the thing that confuses people more than actually the finite difference stuff. But we'll get there eventually. Okay. All right. So let's start by talking about how we can actually discretize our domain. Okay. Yeah, a lot of the people that have stuff named after them were definitely super nerds. So Laplace is one, but I think the one that has his name everywhere is Euler or Euler, or depending on how you how you pronounce the name. Okay. Okay. And so just like before, we're going to start with kind of a general 2D domain. Okay. All right. And so just for the sake of just for simplicity right now, I'm going to go with a square domain. Okay. And remember, when I say discretize it, what I mean is I'm going to break this up into a lot of smaller shapes and grid points. Okay. And so we're going to end up with a domain that looks like this. Okay. Where each of these, vertices right here are the nodes of our mesh. Okay. Okay, so this is a 2D grid. Right. So basically, we're going from like a slice of cheese to a waffle. Okay. And so remember, this is always a a necessary step whenever we're doing any kind of computational work, right? And so in 1D, remember, we've took our line and we broke it up into a bunch of smaller lines. Here, we're taking a 2D domain and breaking it up into a bunch of shapes. Okay. Okay. And so the interesting thing about 2D domains is that we're no longer limited to just one kind of shape, right? Because with a line, there's only so much you can do with a line. You can have a long line, you can have a short line, you can have somewhere in between. But in 2D, we can really start to be creative with the shape. So, we could have domains that look something like this. Okay. And so that's a perfectly valid 2D domain. You might have something that looks like this. Okay. Right. And so going to 2D really opens up these possibilities for us, because now we can make a lot more realistic geometries. Okay. It's just that as the domain gets more and more complex, it does tend to get a little bit harder to simulate, especially when we have to go and apply boundary conditions. Okay. But for the sake of just deriving a theory and just keeping things simple, we're going to stick to just this square domain right here. Okay. And so, just keep in mind that all other types of domains are possible, but for just this class, we're going to focus mainly on these kind of square domains. Yeah. Computational waffle cooking. Now I want waffles. Okay. Any questions on this so far? Okay. And so, we're going to start, really diving into this. So I really want to emphasize, the thing that's really important when you're doing 2D simulations is that you really need to stay organized. Okay. And so, because there's going to be a lot of things going on, because there's going to be a lot of numbers and a lot of parameters flying around. So you want to really make sure that you stay organized, with everything. Because if you can stay organized, that's even more than half the battle at this case. So I think it's more than 60% of the battle. Okay. All right. And so with that said, let's start, putting some names to all these things and kind of specifying things. Okay? So let me draw our waffle again. Okay. And so here is our 2D domain. And let me specify some things. Okay. And so we'll call the horizontal length of our domain, we'll call that Lx. Okay. And then the vertical length of our domain, we'll call that Ly. Okay. And so that's simply just kind of the physical lengths of our domain. Okay. Right. And so that's very similar to in 1D, where we had to specify kind of the physical length of the domain that we're looking into. Okay. In addition to this, we are going to define two more parameters here. Okay. All right. So first, we're going to define nx. And so nx in this case is going to be the number of grid points in the x direction. Okay. And so the way that you obtain the way that you obtain nx is that you simply just count you go horizontally across and you count how many nodes that there are. Okay. And so in this case, we have 1, 2, 3, 4, 5. Okay. And that's going to be the same. So since we have a rectangular domain, that nx is going to be the same, no matter what level you're at in the rectangle. Okay. And so in this case, our nx is equal to 5. Okay. And so in addition to nx, we're going to define ny. And so ny is simply going to be the number of grid points in the y direction. Okay. And so in this case, let's go ahead and count the number of grid points in the y direction. Okay. So let me kind of erase these for a second. All right. And so in this case, we have 1, 2, 3, 4, 5, 6. Okay. And so our ny in this case is 6. Okay. Because we have 6 grid points, counting upwards. Okay. So those numbers are important to know. All right. And so the next parameters that we'll define is we need to define the grid spacing. Okay. And so remember, in our 1D case, the grid spacing was basically just the physical distance in between each of our points. Right? In this case, we're going to have two different grid spacings. So we're going to have a grid spacing in the x direction and a grid spacing in the y direction. Right? Okay. And so in the x direction, those are, that's going to be the distance between successive horizontal points. We'll call that delta x. And the way that we can compute delta x is we can compute it based on the parameters that we have already, okay? And so the way that we compute delta x is going to be Lx, okay, or the length of the domain in the x direction divided by nx minus 1. All right. And remember, the reason we do -1 is because since we have 5 grid points, we have 4 spaces in between each of the nodes, right? So this is space A, space B, space C, space D, okay? And what we want to obtain here is the length of those different spaces, right? Okay, and so that's delta x, and we're also going to have delta y, and so this vertical distance between grid points is delta y. And so the way that we can obtain that is going to be Ly divided by ny minus 1, right? And so those are going to be our two grid spacings, okay? All right, any questions on this so far? Okay. And so what you'll see is that, when we start to develop MATLAB code, these are quantities that you have to define kind of at the top of the code, okay? Because that basically defines what your geometry looks like. Okay. And so now that we've kind of talked about kind of the basic geometrical parameters, let's talk about node numbering. In other words, labeling the nodes. Okay. So this is a point that was kind of glossed over a little bit in the 1D case, but let me show you what I mean by in the 1D case. And so in 1D, after we discretize a domain, what you should have noticed back then was that each of the different nodes in our grid had a unique ID number. Right? And so let me draw a line like this. And so what we did was we labeled all the nodes, right? Such that they each had, a number associated with them, right? And so going from left to right here, we had 1, 2, 3, 4, 5, 6. And these numbers actually served several different purposes. So, the first purpose is just to know, which node is where. But, if you remember when we put together our linear, set of linear equations, right? So we had our matrix A times X is equal to B. These node numbers also defined what rows in the matrix to put our equations. Okay? And so just to kind of refresh your memory, remember the way that we obtained our system of equations was like this, right? And so for a 6-node grid, we'd have different equations for each of the different I values, right? Where I was our node index. And so, for each of the different I values, depending on whether we're at an interior node or at a boundary node, we had an equation that basically governed the physics of that node, okay? And then those equations turned into our system of linear equations that we solved in MATLAB, okay? And so in 2D, none of this changes. So in 2D, we still are going to get the same thing. And so we want to get a system of linear equations. It's just that the way that we number the nodes is a lot more complicated, okay? Because we don't have just a simple line of numbers anymore. Now we have things that go in 2 directions. And so how you choose how to number the nodes is, you have to really be consistent with that, and you have to, remember how you did it. And so as we're going through this, I'm going to show you how I number the nodes, just because that's the scheme that makes the most sense to me. But you're free to use whatever scheme that you want, as long as you kind of make all the subsequent adjustments. Okay. Okay. So let's jump into that. All right. So let me draw our waffle again. Okay. So let's say that we have a grid that looks like this, and then we have all the grid points as well. Okay. Right. And so what we need to do is we need to assign a unique ID number to each of these nodes. Okay. Right. And so you can choose to do this however you want. But this is the scheme that I'm going to use moving forward. Okay. So question. So why not assign them an element like in a matrix? And so we don't want to label the elements here because that's going to be for a different method. So that's typically what you do in finite elements. But since we're doing finite differences, we're focusing specifically just on a grid points. Yeah. Mm-hmm. Okay. And so here's the scheme that I use. So I start in the lower left, and I give that a ID number of 1. Okay. Then from there, I move horizontally across. So I go 1, 2, 3, 4, 5. Okay. And then once I reach the end, then I move on to the next row. Right. So then we go 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Right. And so since we have 20 nodes in this mesh, we can see that our linear system, or our system of equations, is going to have 20 different equations. Okay. Right. And then once we write out the finite difference equations for each of those nodes, we're going to refer to them according to these ID numbers. Okay. Okay. All right, so that from that perspective, this is really useful for writing the equations, okay? But this form right here isn't really useful for just keeping track of where the nodes are located, right? Like if you kind of just closed your eyes and when you weren't aware of this grid, and I asked you where is node number 13 in this grid, right? You wouldn't know because it could be anywhere, right? Because you only just have one number. And so another useful way to kind of characterize the locations of these nodes is to use what I call like IJ coordinates. Okay. And so when you're doing these problems, it'd be useful to kind of draw the grid kind of twice. And so it'd be useful to draw the grid once with all the unique identifiers, and it would also be useful to draw the grid using these this type of, nodal coordinates. Okay, so let me draw the grid again, and let me make sure that I make the grid the exact same size. Okay. So we have 2, and then 3. Okay. And so all I'm doing is just kind of redrawing the same grid here. But what I'm going to do instead is I'm going to label the nodes according to their kind of, you can almost think of them as their x, y coordinates. Okay. Because what we have here is basically a coordinate, a Cartesian coordinates, right? And so we're basically going to assign, we can basically assign an XY coordinate to each one. Okay. Right. And so, so a couple questions in the chat. So do I mean that we're going to vectorize them? So I'm not sure exactly what you meant by vectorize, but basically we're going to assign, coordinates to these. Yeah. And so another question, why do we use ij, not xy? And we use ij because you'll see it's easy to correlate basically ij coordinates with their ID numbers. Okay. Okay. And so their ij coordinates, so this will be like 1, 1 right here. Okay. So basically, x coordinate of 1 and y coordinate of 1. This will be coordinate 2, 1. This is 3, 1, 4, 1. And 5, 1. Okay. Right. So node 13, yes, node 13 is 3, 3. Yeah. So node 13 right here, this is 3, 3. Okay. So it's the third. You go, in order to basically reach that, you go 3 nodes over in the x direction. You go 3 nodes vertically upwards. Okay. And so you can think of these as like their x, y coordinates. It's just that I use just integers just because it's a lot easier to correlate these with their ID numbers. Okay. And so let me just fill in a few more just so that you can get the idea. Okay. And then this right here would be 1, 3. This is 2, 3, 3, 3, 4, 3, and then 5, 3. Okay. And so, when we're doing these problems, I want you guys to keep these 2 grids in mind. Okay. And so on the top here, we have the grid in ID number form. Okay. And on the bottom right here, we have the grid in IJ coordinate form. Okay. And a lot of the bookkeeping that we're going to do in writing a finite difference scheme for this, or in implementing this in MATLAB, is we need to write basically a formula that relates both of these different ways of expressing the grid. Okay. And I'll do that on the next page. Okay. Any questions on this? Okay. Okay. And so what we want is we want a formula that's going to relate the ij coordinates of a node with its ID number. Okay. And so I'll give you the formula that I have for my scheme. But remember, if you're going to use a different scheme, your formula is going to be different. Okay. And so the formula for this is going to be ID is equal to J minus 1 times NX plus I. Okay. Okay. And so the way to use this formula is that you're going to plug in I and j for a specific node, and then you're going to get their ID number from that. Okay. Right. And the reason, the reason this formula takes this form is that, it's because of how we number the nodes. So remember, the way we number the nodes is we started ordering them horizontally first, and then we went up, when we needed to add another row. Okay. And so this is basically the formula that describes that. Right. So then, yes. Right. So question is, so this is why we don't use XY, because we have an X value associated with N. Yes, that's correct. So basically when you're writing these programs, it's a lot easier to keep track of how many nodes you have in a certain direction. And so that's why we use the IJ coordinates, just so that you can basically say that this is the fourth node in this direction. Yeah. Yeah, so I told you guys, it's a lot of bookkeeping and a lot of kind of extra infrastructure, and it kind of seems really annoying at this point. But trust me, once we start writing the codes for these and developing the equations, all of this work is going to pay off, because it really helps to kind of implement the finite difference scheme, in a very organized and kind of systematic manner. Yeah. No, we're not going to do any. I don't even know what phasors are. So we're not going to do that. Yeah. Oh, okay. Yeah. So this is not imaginary numbers. So this is basically just you can kind of think of them as the integer coordinates, but we're not going to do any imaginary number stuff, because honestly, I don't really understand imaginary numbers either. Okay. Okay. All right. So one more thing that we have to define is we have to come up with a formula for the total number of nodes in our grid. Okay. And compared to all the other stuff we've been doing, for the last 10 minutes, this is relatively easy. So, we're going to have a formula. So we'll call that n tot. So for n total, okay. And this is simply just going to be the product between nx and ny. Okay. Right. And so to get the total number of nodes, you just take, the number of nodes that you have in the x direction, the number of nodes you have in the y, and you just multiply them, and that gives you the total number of nodes. Okay. All right. So a lot of parameters, I know, but it's it'll help us a lot. Because because ultimately what our goal is to set up a linear system equation. Oops. Okay. And so if you kind of relate this back to when we did our 1D case, we want to set up a system that looks like this, okay, where we have a matrix A, which contains all the coefficients for our, our linear equations, X, which is our solution variable, and B, which is our right-hand side forcing. That's where we put all the kind of the source terms and all the boundary conditions, okay? All right. And so when we define these matrices, or we define their size, right? So remember, the way that we do this in MATLAB is we use the zeros command. And when we use the zeros command, we have to specify the size of these data structures. Okay? And so A here, which is our matrix, this is going to be a matrix that's n tot by n tot. Okay. And so that tells us basically we're going to have n tot equations and n tot unknowns. Okay. X is going to be a vector, and so it's going to be n tot by 1. And then B is also going to be a vector as well, so it would be n tot by 1. Okay, so these are the sizes of our matrices and vectors. Okay. And so, you know, on Monday when we're writing out the MATLAB code, you know, remember one of the first things that we do is we use the zeros command to create kind of empty spaces where we're going to fill in the coefficients. And so this is basically the size of those data structures. Okay. Okay. Any questions on this before we start applying finite differences? Okay. All right. Oh, question? 5 by 5. That's if you have a grid with five nodes. And so in this particular case, you know, where we have 20 total nodes, here nx is equal to 5 and ny is equal to 4. Here a is going to be 20 by 20. Oh, previous example. Which one?
You were right. I thought it was a 5 by 5.
Okay. Okay. Yeah. Yeah, so you have to be careful here too, because, you know, because we're doing a 2D rectangular grid, this thing itself kind of looks like a matrix, right? So, you know, when you're doing the matrix, it's, you know, you're not putting in the size of the grid itself, but you're putting in the size of the matrix is determined by the number of nodes that you have, okay? And so, you know, it's always good to remember, you know, that the matrix that we're going to write represents all the different equations and all different unknowns that we have. And so since our grid here has 20 nodes, that means we're going to have to write out 20 different equations that govern its physics, right? And so with 20 equations, that means our matrix has to have 20 rows and 20 columns, okay? So it's always kind of it's always good to kind of keep those things in mind. Okay, and so now let's actually start applying finite differences to our diffusion equation. So this is applying our finite differences to our 2D diffusion equation. Okay. And so let me write out the 2D diffusion equation again. Okay. And so what we're going to do from here is we're going to apply finite differences to both of these derivatives. Okay. Keeping in mind, you know, that these derivatives, even though they're both second order derivatives, they're derivatives taken in different directions. Okay. And so let's start with partial squared x partial x squared, or partial squared phi partial x squared. Okay. Right. And so when we apply finite differences to that, we get the following. Okay. And so we're going to have phi I plus 1, comma j, minus 2 phi I, comma j, plus phi I minus 1, comma j. Okay. Oops. And all of this is divided by the grid spacing in the x direction. So this can be divided by delta x squared. Okay. All right. And so this is nothing more than just our finite difference equation for our second order derivative, right? And so in the 1D case, remember, we applied this once for that equation, and this is what we get, okay? And so what you see here is that, you know, we have two coordinates now, right? And so the phi no longer is just, you know, I. And so now we have phi at I, comma j, because, you know, there's coordinates in both. And this is, you know, and this is another reason why we use the ij coordinates for, you know, our 2D grid, right? So that we can kind of basically easily plug them into this expression here, okay? Right. And so another thing you should notice about this is that, you know, when I'm making the changes in the nodal IDs, notice that I only did that for the I coordinate, right? So the j coordinate is all the same in this one. So it's all j. And that's because this is a derivative in the x direction, not the y. And so, you know, we don't change in y at all. And so in contrast, let's look at the finite difference approximation for the y derivative. Okay. And so we have partial squared phi, partial y squared, right? And so the formula for this is going to look very similar. Okay. And so we're going to have phi I j plus 1, okay, minus 2 phi I comma j plus phi I j minus 1, all divided by delta y squared. Okay. And so again, we have our finite difference equation here. It's just now that we're applying it in the y direction. Okay. And so now we're making changes with respect to j instead of I, and then in the denominator there we have delta y squared. Okay. All right. And so what we have to do from here is just take these equations and plug them into our diffusion equation up here. Okay. And so what we get from that, when we just plug it in, we get phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j, okay, all divided by delta x squared, okay, plus d squared phi dy squared, which is phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1, okay, all divided by delta y squared, okay. And then all this is going to be equal to our source term, which is q, and I'll just leave it as q for now, okay. Actually, let me label this. So I'll call this q at I comma j, okay, because it's going to be our source term evaluated at the I and j nodes. All right. Okay. All right. So all I did basically there was just plug in our finite difference approximations for the derivatives back into our 2D equation. Right. And so technically this is right here, but I'm going to simplify this a little bit just to help us with our calculations. And so let me apply an assumption first, just so we can simplify this. Okay. And so let me assume that the grid spacing in the x and y directions are the same. Okay. And so basically we're going to have delta x is equal to delta y. Okay. Then I'm going to shorten this and just call it delta. Okay. Right. And so that should help us simplify this pretty significantly, because now we can, if we want, we can put these all into the same denominator. But what I'm going to do actually is I'm going to take delta squared and multiply by both sides. Okay. And so what that'll do is that'll allow us to write this equation without any fractions or any kind of division, which is a little bit easier to write, and it will allow us to simplify the left-hand side a little bit. Okay, because if you notice, both of the finite difference approximations for our two derivatives here have this phi I comma j term. Okay, and so if we assume the grid spacing the same and we move it over to the side, we can basically combine these two. So it's not that much of an improvement, but it at least cuts down on one term on that side. Okay. And then once we do that, I'll write down kind of the equation that you're basically going to use in deriving these kinds of equations. Okay. All right. Any questions on this before I write out that equation? Okay. All right, and so if we perform those steps, so we multiply both sides by delta squared, we end up with the following equation, right? So we're going to have phi I plus 1 comma j plus phi I minus 1 comma j plus phi I j plus 1 plus phi I j minus 1 minus 4 phi I comma j is equal to q at I comma j times delta squared. Okay. And so this is our finite difference equation for 2D diffusion. Okay. Right, and so the way that we're going to use this equation is basically the same as our finite difference equation back in the 1D case. And so we're going to apply this at each of the different I comma j nodes in our mesh. Okay. Okay. And what you'll see is that you'll be able to apply this equation to all of the interior nodes, but the nodes that are on the boundary, you won't be able to apply this. But we'll talk about the boundary conditions in a bit, because boundary conditions is another thing that's going to be, pretty complicated. Okay. Okay. And so another name that's given to this type of equation here is the 5-point stencil. Okay. And so the reason for that is that in this equation, we need 5 different points. Okay. And so let me draw a node right here. Okay. And so let's say that this is the I comma j node. Okay. And so in order to apply this equation, we're going to need to have neighbors to the left, to the right, above it, and below it. Okay. And so the ij coordinates of each of its neighbors are given by the following, right? So its neighbor above it will be I comma j plus 1. Its neighbor below it will be I j minus 1. Okay. Its neighbor to the right will be I plus 1 comma j. And its neighbor to the left will be I minus 1 comma j. Okay. And so, basically what this shows is that in order to compute the diffusion equation on a finite difference grid in 2D, we're going to need to borrow values from all of its neighbors. Okay. Okay. And so actually, if you want to kind of rewrite this equation or relabel these nodes to kind of help you remember, I think that'd be useful, right? And so on the first term of this equation, we have phi at I plus 1 comma j. And so this is our right neighbor. Okay. Then we have phi at I minus 1 comma j. And so this is our left neighbor. Okay. Then we have phi at I comma j plus 1. So this is the top neighbor. And then phi at I comma j minus 1. This is the bottom neighbor. Okay. And so basically to write out the finite difference approximation, you need all of these neighboring values to write out the equation. Okay. All right. Any questions on this? Okay. All right. So this is all this is good right here, but right now this equation is not in the most useful form because now it's in IJ coordinates. Okay. So what would be more useful is if we wrote this equation using its ID numbers. Okay. Because its ID numbers, the ID numbers is ultimately where we want to be working with these kinds of systems, because eventually we're going to have to put all these guys into our linear system of equations, right? And it would be more useful to have all of these things in terms of its ID numbers versus its IJ coordinates. So the IJ coordinates are kind of useful to help to know where a node is physically located, but when we need to go and form the equations, it's more useful to have them in terms of their ID numbers. Okay. And so with this in mind, let's use our ID equation that we had earlier to write out the ID numbers for not only the node in question, but also all of its neighbors. Okay. And so, I want you guys to keep in mind kind of this grid right here. And so we basically want to write ID numbers for all of these guys. Okay. And so let's start with the IJ node. And so for the IJ node, since we know I and J, we can just simply use the equation for this guy. So ID is simply going to be J minus 1 times NX plus I. Okay. Okay. So fairly simple. Okay. And so now let's write out the ID number for the left neighbor. Right. And so for the left neighbor, we know that relative to I comma j, it's going to have I minus 1. Okay. And so let's write out the same ID equation, but instead of I, let's substitute I minus 1. So ID is going to be j minus 1 times nx plus I minus 1. Okay. Okay. And so similarly for the right neighbor, we're going to have instead of I, we're going to have I plus 1. Okay. So again, ID is equal to j minus 1 times nx plus I plus 1. Okay. Okay. Where you can see that the only thing that are changing in these are kind of these last terms right here. Okay. Okay. All right, so now let's write out the equation for the top neighbor. So for the top neighbor, relative to I comma j is going to have j plus 1. So let's take the same equation. Instead of j, I'm going to plug in j plus 1. So we have ID is equal to, we're going to have j minus 1 plus 1. So we're just going to have j, okay, times nx plus I. Right? And then finally, let's write out the ID equation for the bottom neighbor. And so for the bottom neighbor, relative to I comma j, it's going to be j minus 1. Okay. And so let's plug in j minus 1 into the equation up there. Okay. And so we're going to have j minus 1 minus 1. And so that's going to be j minus 2 times nx plus I. Okay. And so in the last two equations, the only things that are changing are the values of j. Okay. So the reason, you might be kind of asking yourself, why did I just spend the time just to do that? That seems kind of really silly and really pedantic. But again, with these problems, it really helps to stay really organized and really write everything down. Okay. And, once we go and implement the code, these 5 lines right here, these are going to be 5 lines that will guaranteed be in all of your 2D codes. Okay. So this will be in your MATLAB code. Okay. Because remember, when we're writing code, we're basically writing instructions for MATLAB to kind of solve these problems for us. And so we want to, basically spell it out as explicitly as we can for them. Okay. And so for something like this, if we have a node with coordinates I comma j, it's easy for us to kind of look at that and say, I know what its ID number should be. And once we do an example on the next page, you can do that. But when we write this in the computer, the computer has to be told explicitly, everything that it needs to do. Okay. Okay. Any questions on this before we do an example? So question. So does this pull data off an array using the ID numbers? You can. And so, eventually, once you solve, because right now there's no solution there. And so eventually we're going to solve this equation for all of the phi values at all the nodes. And so eventually, you'll be able to pull the numbers off of the array. But for now, remember, the reason we're doing this is we're just setting the coefficients in our left-hand side matrix, right? And so basically, remember, we're basically setting up the algebraic problem for the computer to solve for us. Yeah. Mm-hmm. Okay, so let's do an example because we've spent all this time talking about ID numbers and I's and J's and stuff like that. So I think it'd be useful to kind of take a step back and do an example, right? And so let's say that we have a 4x4 grid in our mesh. Okay. Okay. And so we're going to have we have a square grid that looks like this. Okay. And so we're going to have 16 points overall, so 4 points in the x direction and 4 points in the y direction. Okay. So let me go ahead and number all of these nodes. Okay. And then let me draw the same grid, but let me draw out the ij coordinates for each of the nodes. Okay. 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 And so the ij coordinate in the bottom left is going to be 1, 1. This is going to be 2, 1. This is going to be 3, 1, and 4, 1. Okay. Then we're going to have 1, 2, 2, 2, 3, 2, and 4, 2. And then we're going to have 1, 3, 2, 3, 3, 3, and 4, 3. Okay. Then we have 1, 4, 2, 4, 3, 4, and 4, 4. Okay. Okay. And so what we want to do in this problem is we want to write out we're going to write out the finite difference equation for nodes 6 and 10. Okay. Right, so I'm going to do it. I'm going to do this in two ways. Okay, and so the first way I'm going to do it is kind of just intuitively from the you know from the picture here, and then the second way I'm going to do it is I'm going to use all the formulas that we just wrote out here for all the left neighbor, right neighbor, top neighbor, and bottom neighbor. Okay, all right. So let's start with the intuitive way. So let's start with node 6. Okay. And so we know that when we write out the finite difference equation, we're going to use, the values to the left, to the right, above, and below. Okay. And so let's locate node number 6 in our grid here. And so let me draw the stencil here. Okay. Right. And so what I've highlighted right there with that kind of little plus sign are all the neighbors for 6. Okay. And so let's do that. And let's fill in this equation that I have right here, right? Because remember, we're going to have, the right neighbor, the left neighbor, the top neighbor, the bottom, and itself, okay? All right, so we can see from the diagram here that the neighbor to the right of 6 is node number 7, okay? So we're going to have phi 7, okay? Then we're going to write out the neighbor to the right, which is 5. Okay. Then we're going to write out the neighbor to the top, which is going to be phi 10. Okay. Then we're going to do the neighbor to the bottom, which is phi 2. Okay. And then we're going to subtract 4 times, the node itself. And so the node itself in this case is 6. Okay. And we didn't specify qij here, so we're just going to do qij delta squared. Okay. And so this right here is the finite difference equation for node number 6. Okay. Right. And so we did that one just purely visually. So we just looked at the grid with our eyes, and then we saw which neighbors were on the top and the bottom and the left and the right, and we just kind of filled those into the equation. Okay. All right. And so now what I'm going to do for node number 10 is I'm going to do the same thing, but I'm going to apply the ID equations. Okay. Right. And what you'll see is that you'll get kind of the exact same thing. And for now, it's going to seem like we're going to get the same thing with 10 times the amount of work. But this is to put it in this form is really necessary because this is what the computer is going to have to interpret, because the computer can't look at a picture and and really tell where the neighbors are. For the computer, we have to spell it out using equations. Okay. And so for node 10, we can see from the diagram here that node 10 corresponds to I is equal to 2 and j is equal to 3. Okay. And so let's write out the ID numbers for node 10 itself and all its neighbors. Okay. Right. And so let's start with the ID number for 10. Okay. Which is redundant because we know it's node 10, but let's plug in I is equal to 2 and j is equal to 3 into our ID equation. Okay. All right, so our ID equation is j minus 1, and so we're going to do 3 minus 1, okay, multiplied by nx, and so in this case nx is 4, okay, because we have 4 nodes in the x direction, and then to this we're going to add I, where I is 2 here. Okay. Right, and so we just performed this arithmetic, so we're going to have 3 minus 1, which is 2, times 4, which is 8 plus 2, and that gives us 10. Right. And so, I know it's silly to kind of write an equation for this for something that we already know, But remember, for the computer, we have to do this kind of explicitly for them because they're not going to be able to look at the picture. Okay. All right. So now let's write out the equation for the left ID. And so for left ID, we're going to have j minus 1. So we're going to have 3 minus 1 again. Okay. Times nx, where nx here is 4. And then to that, we're going to add I, which is 2 minus 1. Okay. Right. And so remember, we do I minus 1 for the left neighbor. And then what we get from this is 9. Okay. And you can see from the diagram, indeed, ID number 9 is the left neighbor for node 10. Okay. Okay. All right, so now let's compute the right ID. So the right ID, we're going to have 3 minus 1, just like before. So that's j minus 1 times nx, which is 4 plus 2 plus 1. Okay. And then from that, we get 11. And so we check back with the diagram and we see indeed that node number 11 is the right neighbor for node number 10. Okay. All right, question. So when you are on node 14, you don't have a top neighbor. Yeah, that's a great observation. And so, that's true for basically all of the nodes that are sitting on the exterior of our domain. And so if you think back to the 1D case, when we had those cases where we're on the domain, we don't apply the finite difference equation. What we do instead is we apply a boundary condition, right? And so, we'll talk about how we can apply boundary conditions in 2D as well. Yeah, because that's definitely an important part. Okay. Okay. Any questions on this so far? Okay. All right. So now let's write out the equations for the top neighbor and the bottom neighbor. All right. So top ID. So our top ID, our equation for that is going to be j times nx. And so we have 3 times nx, which is 4. Okay. Remember, we're plugging in j plus 1 into our equation. Okay. Plus 2. And this gives us 14. Right. And so if we check back into our diagram here, we can indeed see node 14 is on top of node number 10. Okay. Right, then we can compute the bottom ID. Okay, and so for bottom ID, we're going to do 3 minus 2 because our j coordinate is 3, and we're going to subtract 2 times 4 plus 2. Okay, and this gives us 6. Okay, and so we look back at our diagram, and we indeed see node number 6 is the bottom neighbor for node 10. Okay. Okay, and so now that we have all these ID numbers, we can just simply write them all out together. Okay. Right. And so we're going to phi 9 for the left neighbor plus phi 11 for the right neighbor plus phi 14 for the top neighbor plus phi 6 for the bottom neighbor minus 4 phi 10 is equal to qij times delta squared. Okay. And so exact same result is just that, we went about it in a different way, using the equations. And so, it might seem really tedious and really, pedantic, but, you'll see on Monday when we actually implement this in code, this is exactly what MATLAB needs in order to compute these ID numbers. So it needs these equations because that's like the code of MATLAB, right? Yeah, it is tedious, but remember for when you're writing code, all you have to do is basically set up the problem for for MATLAB, and MATLAB is going to do all the tedious stuff. So the only thing you have to do is just to show MATLAB how you can actually compute these things, and that's kind of the purpose of all of these formulas. Yeah. Right, exactly. So when we actually write out the code, we're going to do all of this in a loop. And so setting up the first loop, we're going to use equations like this, but for all the other nodes, it's all going to be encapsulated within that loop. So in the end, you actually end up not writing that much code because the loop is going to handle most of that for you. Yeah. Mm-hmm. All right. Any questions on this before we start talking about boundary conditions? All right, so let's talk about boundary conditions, okay? Because Juan made a great point earlier that, if you're going to apply this finite difference equation, you can only do it on what's called the interior nodes, okay? Okay, and so by interior nodes, what I mean is nodes that have a neighbor on every single side, okay? And so in this case, there's only 4 of them because there's only 4 nodes on the interior. But if we look at nodes like maybe 3, maybe 4, maybe 8, maybe 14, all of these are missing at least one neighbor, right? So if we consider it like node number 8, okay? Node number 8 doesn't have a right neighbor because it's right on the right edge of the domain, okay? And so for all of these nodes that sit on the edge, we have to apply a different equation, that's going to be defined by its boundary condition. Okay? Okay. And so the unfortunate thing is that boundary conditions in 2D are a lot more complicated than they are in 1D. Because in the 1D case, we only had two boundary nodes, right? We had the left boundary node and the right one. And so in 2D, it's a lot more complicated because now we have a boundary edge, okay? And so, all of these nodes on the left edge, all of the nodes on the top edge, and all of the nodes on the right and the bottom, all of these guys are boundary nodes. And so we have to account for them, with boundary conditions, okay? And as you can imagine, if we refine the grid or we insert more points, the number of boundary points are going to go up, okay? And so this makes things a lot more complicated because we can't just modify two locations in the linear system. We're going to have to modify a lot of them. Okay. Not only that, it's not just going to be the first row and the last row. The boundary nodes are actually going to be scattered all throughout the system. Okay. And so we can say that the boundary nodes, there's probably going to be a lot of them. Not only that, but they're going to be scattered through all the different rows in our linear system. Okay. Right. So this makes things, a lot more complicated. And so what you'll see, once we implement the codes in MATLAB is that we're actually going to need to use loops in order to implement the boundary conditions, okay? And these loops, are going to be separate from our other loop, okay? Okay. All right. All right, so, and in reality too, when you have these 2D problems, you can have boundary conditions that are really, really complex, right? And so if I draw kind of a 2D domain right here, okay, what can happen sometimes is that, for one part of a side, like say from here to here, you might have a certain kind of boundary condition, okay? And then for another part of it here, we might have another boundary condition. And so it's you can see it's really starts to get complicated. But for the purposes of this class, we're going to assume that all the boundary conditions on one side of our domain are all going to be the same. Okay. And so in total, for a rectangular domain like this, we're going to have 4 boundary conditions. Okay. So we're going to have boundary condition 1, we'll say on the left side. We're going to have boundary condition 2 on the bottom, boundary condition 3, and then 4. Okay. And then all the nodes on that side of the domain will have that same boundary condition, okay? So how will we get the boundary condition for the middle outer node? Which one do you mean? Oh, so you mean like in this equation right here, one of these would be on the boundary, like for phi 14, right?
No, you meant like there was two boundary conditions at the bottom.
Mm-hmm.
How would you get the
Oh,
boundary condition for the middle node?
right. So
Well,
so that so so that's why for this class we're going to ignore that, and so for this class we're going to assume that everything on the same side has the same boundary condition, just for kind of simplicity, because like once you start making things more complicated, it gets to be kind of crazy. So just for the purpose of this class, we're going to assume everything on a side is the same. Okay. And so where things get complicated are at the corners, actually, right? And so the corners kind of exist on two sides at the same time. And so the question is, which boundary condition do we apply there, right? And so, since we're out of time, I'll leave you on that cliffhanger. So, once we pick this up on Monday, we'll talk about how do we actually apply these boundary conditions and how do we actually deal with the corner nodes, right? And so tune in next week on computational heat transfer, and we'll find the answer, right? Maybe finally Goku will defeat Vegeta next week, right? Okay. So thank you guys. Thank you guys for tuning in for the class today. And so, we're going to finish up the 2D diffusion equation on Monday. So definitely look forward to that. And we're going to see how this is implemented in MATLAB on Monday as well. So make sure you have MATLAB ready for Monday. Okay. Right. And so, yes, this stuff is on the homework. So, definitely, you're going to need the stuff on Monday. And I think the homework is due a week after that. And so it's going to be due on March 1st, I believe. Yeah. Okay. All right. So thank you guys for tuning in today. Have a great weekend. This is not a long weekend, unfortunately, but I'll see you guys on Monday.
Thank you.
Thanks, guys.
Oh, Professor?
Yes.
So for the homework too is due on the 24th, right? Not March 1st?
Let me check. It should be.
I think it's on the 24th right now.
Oh, it's the 24th.
Yeah.
Oh, okay. Oh, sorry about that. So it should be on March 2nd, or March 1st, I believe. Yeah, because usually, after I finish the lecture material for homework, I like to give you a week after that. So let me change the due date for that to be March 1st. Yeah.
Awesome.
Yeah,
Thank you.
Yeah, thanks for letting me know, and I'll send an announcement for that as well. And Con, I got your email with your homework code, so I'm going to take a look at it basically right after this, and I'll give you feedback on it. Yeah.
Okay, cool. I'm gonna be at your office hour tomorrow, so we can discuss that.
Okay. Yeah. So I'll send you the feedback now, but if you have questions tomorrow, you can come to the office hours as well. Yeah.
Awesome. Thank you, Professor.
Yep. Mm-hmm.
Bye.
Bye. No, I love it. Yeah, keep posting it. I love to see the Discord server active like that, especially with the meme. So I think it helps keep everything light. So I appreciate that. Mm-hmm.